All right, welcome to this example. In this example, we're going to look at how phase changes and heating go hand in hand and how we can calculate the energy required to heat a block of ice to steam, in other words, water vapor at a specific temperature. So the question that we want to look at is we calculate the energy needed to convert a certain amount of ice at minus 10 degrees Celsius to steam at 120 degrees Celsius. You may assume that the heating is the only cause of energy transfer between the water and the surroundings. Assume that the density of water is exactly 1 gram per milliliter. So in other words, basically we're told all the energy given or the system requires will be coming from the surroundings, and it'll be exactly a perfectly closed system. In other words, the only source of heat is from the surroundings, and you do not have to worry about any work that may be there or any other causes for energy loss. So how do we determine what is the energy required? What are we looking at? And the best way to imagine that is if we take a block of ice and we heat it on a Bunsen burner, say for example, the ice is going to heat up until it gets to its melting point. Once it melts, it's going to change. Well, then there's going to be a period where we have ice and water in combination, and some stage where we only have water. Then the water is heated, and at some point the water will start to boil, and then we will start seeing the vaporization until there's only water vapor left, and that gas is then going to be heated until 120 degrees Celsius. That's why it's important that it's a closed system, because otherwise the gas will escape and then things get a bit difficult. But so that's the basic idea that we have in mind. So let's try to illustrate that just initially for ourselves at least by plotting, well, let's say it's the temperature in degrees Celsius against the heat. So the temperature increases that way, heat increases that way. So we're adding heat to a system. We're not extracting the heat. Our starting temperature, we're told, is minus 10 degrees Celsius. So here's minus 10.0 degrees Celsius. And that's where our block of ice starts. So we're going to heat this block of ice until a certain temperature. And at which temperature or at which point the system is then going to want to undergo a phase change. And that phase change is from solid to liquid. Right. So that's our first, this should be flat. Let me try and draw it flat. Yeah, there it's nice and flat. So our first process is just where we heat the ice. And that heating process is going to require a certain amount of energy, so heat. Let's call it Q1. And importantly, we know we only have ice in this situation. So it's only heating of ice. The ice is only taken from minus 10 degrees Celsius to its melting point. And what is its melting point? Well, melting point of ice is 0 degrees Celsius. And at that point, we have 100% solid, but by adding more heat, we'll eventually end up with a liquid. So this area here is, of course, where we melt the ice. Okay, and this line represents, so we go from solid to liquid, but in between, it implies there's going to be ice, so in other words, solid plus liquid in some stage. Also, the heat added during this period, we're going to call it Q2. So that's what we call that. Now, what happens after the ice has melted, that we have pure liquid? Then, of course, we keep on heating it until we get to 100 degrees Celsius, because water boils at 100 degrees. So there will be some period where we're simply heating the water. So we heat liquid water. And we call this heat that we add Q2. Okay, so we're going from liquid here to just heating the liquid. So it's just warming up the liquid. If you put a pot on the stove with some water in it and you start to heat it, it's not going to boil immediately. It's going to take some time to heat up. So that's what we're looking at here. But at some point, and that point we commonly know as 100 degrees Celsius, and this graph is now not completely to scale, but it's just to get the idea. So this is 100 degrees, 100.0. At that point, we'll see another phase change. And this time the phase change is from liquid to gas. So we have a phase change where we want to vaporize the water. We'll vaporize the liquid water. And the heat that we require for that, I'm going to call that Q4. Seems like my graph needs to extend a bit. There we go. And then finally, whatever, we haven't used red yet. We're going to heat this gas a tad. So that's its end point. And that's to 120 degrees. So 120. So that's that part, we only have gas left. So in principle, we are heating the gas. Otherwise known as water vapor. Okay. And the heat required to do this, we call this Q5. Right, so that's the process that's happening. We heat a substance in the same phase. Once it undergoes a phase change, we have a plateau, but there's still heat being added. So let's think about how to calculate those things. So how do you calculate heating, or in heating, how do you calculate the amount of heat? In heating, you use the specific heat capacity. So you use the mass of whatever its specific heat capacity and the temperature change. So that is for lines that are diagonal, how you calculate it. For something undergoing a phase change, we know we calculate the heat as the delta H, so the heat of fusion or the heat of vaporization or heat of sublimation or whatever, times the mass. Right, and why can we write that? Because we know this process happens at constant pressure. Okay, what are the other things that we know? Well, we know there's phase changes, so it's important how does the mass work? We start with 72 grams of ice. So what we assume, because it's a closed system, our mass stays the same. So the mass of the ice will be equal to the mass of the water. Well, water here just means liquid water, which will be equal to the mass of the vapor, or let's call it water vapor. Water vapor. So the mass remains the same. Okay. Now the next thing that we need, so what are quantities that we will need? We will need the specific heat capacity of ice, liquid water, and water vapor. We'll also need the enthalpy of fusion and the enthalpy of vaporization. So where do we get those values? Well, you're going to look it up in your textbook. So your textbook has an appendix, or anywhere really. I mean, you can Google it as well. In general, if you were in an exam situation, you would be given these values, or at least in your data sheet, you'll receive these values. So in some kind of way. So your textbook has a lot of useful appendices. So there's a lot of, so for example, this one covers some calculations. There's one on how do units work. And there's also some useful conversion factors with their symbols. So you can go and check those out to see, for example, what is pressures units otherwise written in SI units, physical constants, etc. We want to get to the part that says something about this is the ionization constants. It's not the selected thermodynamic values. I think I just went over it. It's not this one. Skip it in the previous one. Yes, here it is. So where it says specific heats and heat capacities of some common substances, so it gives you the specific heat, which of course, and the molar heat capacity. So you want the specific heat capacity, which you can look up. So there in the middle, it's water, ice, and steam. And you can also look up the heat of, so the enthalpy of fusion of certain stuff. So for example, there is for water, you see the heat of fusion and you see the heat of vaporization. So that's where I get the values from. So I'm just going to summarize them here. So the specific heat capacity of ice, so solid water, is equal to 2.06 joule per gram per Kelvin. The specific heat capacity of water, so liquid water, is equal to 4.184 joule per gram per Kelvin. And the liquid or the specific heat capacity of water vapor is equal to 1.86 joule per gram per Kelvin. Okay, the other two quantities that we need is the heat of fusion. You might also see it sometimes called Q fusion is equal to 333 joule per gram. And of course, so that's fusion, that is from solid to liquid. So to go from solid to liquid, that is something we'll use. And we also have the enthalpy of vaporization. So delta H vap, which is also sometimes called Q vap, is equal to, not that, 2256 joule per gram. So you can, and of course this is going from liquid to gas. Interesting, I mean, that you can see it takes a lot more energy per gram to get water into the gas phase than it gets into the liquid phase. And that's of course because of the structured order of water and its hydrogen bonds, which is a topic for a later theme. Okay, so now our point is to calculate all these Qs that I listed. So Q1, Q2, Q3, I think that's Q3, Q4, and Q5. So now we just basically grind through the process. So Q1, which is for heating the ice, And we know heating requires then mc delta T. So this is the mass of the ice multiplied by the specific heat capacity of the ice times the temperature change of the ice. And all these values are, so this one is 72.0 gram. This one is 2.06 joule per gram per Kelvin. And this one is going to be 0 degrees C minus 10 degrees C, which ultimately should give you a value of 1483.2 etc. joule. Right, so because we take the ice from minus 10 to 0, we end at 0. So it's minus 10. Yeah, so that's what's going on there. So what's our next step? What is our second heat? Well, that is when we melt the ice. To melt ice, so in other words, for it to undergo a phase change, we use M delta H. So it's the mass of ice times delta H of fusion. And then this is going to be 72.0 gram multiplied by the 333 joule per gram. Why is there no delta T? Because there's no temperature change. And this one is going to be 23976 joule. Next step. Now we have water, so we've melted the ice, so we have water, so now we heat the water. It's going to be heating the water is the mass of the water, specific heat capacity of the water, times the temperature change of the water will be equal to, again, 72 grams, because it remains a closed system, so there's nothing lost, 4.184 joule per gram per Kelvin, multiplied by delta T. In this case, where do we end up? We end up at 100 degrees Celsius. We start at 0 degrees Celsius. And remember, you can write degrees Celsius or Kelvin because the change in either one is the same. And then you should get a value here of 30124.8 joule. Q4 then is the phase change to vaporize the water. So we want to vaporize the water. And that means we use M delta H. So we use the mass of the water times the enthalpy of vaporization. The mass remains 72.0 gram. The enthalpy of vaporization is 2256 joule per gram, equal to 16243.2 joule. Finally, the fifth one is to heat the water vapor. So we heat the vapor. Will be equal to the mass of the vapor times specific heat capacity of the vapor times the temperature change of the vapor. That then equals 72.0 gram multiplied by 1.86 joule per gram per Kelvin. And the temperature changes, we want to get to 120 degrees C, but we start at 100 degrees C. This value is equal to 2678.4 joule. Right. The final step is we need to sum all those heat values, because that is the total amount of heat to go from the left-hand side of this graph all the way to the top there on the right-hand side. So we just we just sum all these quantities. You can like draw something like that, which you call then Q total. So Q total is equal to Q1 plus Q2 plus to Q5, and that should be equal, rounded to three significant figures, 74.5 kilojoule, or 74,500 joule. Okay, and of course you need to answer the question. So then you say, therefore, the total energy, you can write these words out, total energy required to turn ice at minus 10 degrees Celsius to water vapor at 100 degrees Celsius is 74.5 kilojoule. Okay. So that's a very slow way of going through these things. And you know how the graph works. You know this is heat absorbed. Of course, the opposite process can also be done. So then the system just releases heat. Instead of absorbing heat to undergo the phase changes, it releases heat to undergo the opposite direction. So that might be a different way of asking the same thing. All right. Thank you for watching.